Okay, I will talk today about machine learning for accelerated molecular discovery, and I will summarize a couple of research topics and research projects that we did in the last 2 years. But before I start, I would like to acknowledge my still small but growing research group here at KIT, and of course also the funding, who was working on most of the things I'm presenting today. So we are working at the interface of methods development of machine learning methods on the one side. That's why we're also mostly in the computer science department of KIT, but all the methods we're developing are generally built for the purpose to be used in chemistry and material science, both on the simulation side and on the experimental side. So all the things we're working on are somewhere at the interface, more or less closer to methods development or closer to the application in one of these areas. And today I will present 3 specific topics. I will first give some introduction into how we can use actually machine learning models or generally design machine learning models to be used for molecular applications, for materials applications. In particular, I will talk about some of the work and some of the methods developed by Patrick Reiser in the area of graph neural networks. And then I will switch to a topic where we show how we can use such methods in order to drive, in this case, photodynamic simulations to explore reaction mechanisms using machine learning accelerated simulations. And then I'll switch from the simulation to the experimental side and show a research work that we did with Manuel Zotzalas in the last year, where we use machine learning methods to predict synthesis conditions for metal organic frameworks. But this, of course, can be generalized to any other class of molecular compounds or materials as well. So let me start with the first part. How can we represent molecules for machine learning models? What is the best useful way? What are the best models currently? And then later, how can we use them? So as you might all know, there's like a huge chemical space of potential molecules and compounds and materials that we can potentially make. And then in order to design new materials or find new molecules and compounds, we need to explore that space. And this exploration is costly and takes a lot of effort. So if we look at, for example, the PubChem database, which contains a lot of molecules and compounds, we see there's over 100 million, but compared to this 10 to the 60, which is like a rough estimate of the size of chemical space, this is just a very small fraction of the total space that is potentially available and it's just waiting for us to be discovered. So basically all the decades of research in chemistry, of synthesis, of experimental exploration led to this very impressive amount of 100 million compounds, but we need to still speed up to find molecules even faster. So the experimental exploration is very good because it's super reliable and it works. And in the end, if we have a compound, we know it, we can make it and it has the properties, but maybe computational screening can speed it up. And of course, with simulations, we can get orders of magnitude faster exploration. Of course, we need methods that we can rely on, but there's a lot of experimental simulation techniques that can tell us the properties of molecular compounds before we even make them. So this already was speeding up the exploration by orders of magnitude. But a lot of this data that is being generated in simulation is kind of used one time to predict, to make a new data point in some database of a hypothetical compound, but then it's not reused anymore. And there's a lot of data-driven methods, machine learning methods, that can potentially exploit all of the data that is being generated in simulation, also in experiment, of course, and use all of these relationships into that data to even faster predict or estimate molecular properties or predict synthesis conditions and so on, even faster than computational screening efforts. But the big question, of course, is how do we bring together data-driven methods, machine learning methods, with molecules? Because molecules, when we think about them, what they essentially are, they're atoms and bonds, if we want to define bonds in space. So they're like 3D objects consisting of atoms that are somehow connected. And this is not necessarily easily compatible with what is used in classical machine learning methods. We think about neural networks. They have typically consist of layers of neurons, and these layers have a fixed size, so we need to represent a molecule somehow as fixed sized vectors, independent of the size or the shape or whatever of the molecule, to be able to feed that into neural networks, and that's not necessarily a trivial task. There's, of course, also other types of machine learning methods, for example, convolutional neural networks, which are very successful when it comes to analyzing image-like data, video-like data, where the data is basically very neatly arranged in grids of pixels. But molecules are not such objects, so CNNs cannot trivially be used to predict molecular properties. And then there's a lot of success in machine learning for sequence data when it comes to translation, for example, to language, to understanding. And those are recurrent neural networks that deal with sequence type data, and also molecules are not trivial to be represented as sequences, so also this doesn't 100% work. So we need better methods that ideally work directly on that data structure on 3D objects, atoms or points in space. And I will now, in the next couple of slides, show you how we can get there. So one of the ways to represent molecules would be to just break the molecule apart and tell a machine learning model what are the subgroups that are present. And this is the idea of molecular fingerprints. Here we basically make a representation of a molecule in form of a vector, and the vector will tell us what subgroups, what subgraphs of the molecule are present in a certain molecule, in a certain compound. So each of these bits here represents one chemical group. We can either define this using our expert knowledge. We can also define this in an algorithmic way, what pixel or with what entry represents which group. And with that, we can map basically every molecule to a fixed size vector and use this in for machine learning models for typically normal neural networks. But there's no mapping back, for example. So there's some information getting lost when we're going from a molecule to this fingerprint vector. And this loss of information will always reduce the capability or the information content of what is being stored in a fingerprint vector. So maybe this is not the ideal way of representing molecules, even though it's quite intuitive and easy to do. So if we look at that thing, so we went basically from a molecule to its graph, we defined the subgraphs, then mapped this to a vector that told us what subgraphs are present, and then we fed this into a machine learning model to predict properties. So the question is, can we skip this? Can we bring it closer together? And there's another method, for example, that directly represents the full information of a graph in a string. For example, in a SMILE string, which is also mostly used to store molecules in databases, to make them comparable, to make them retrievable, and so on, searchable. There's other representations, for example, selfies, which we developed 2 years ago in Alana Spuruguzzi's group, which are an alternative SMILES representation that's better suited for given machine learning tasks. So here we represent the full graph in form of a string, and then we can use the sequence models that I mentioned earlier, because these strings are basically sequences of characters that encode the molecule. So we can feed this directly into recurrent neural networks in order to then predict molecular properties. The good thing here, this works in both directions. So as I said before, the graph to fingerprint only goes in one direction, so we cannot go back from a fingerprint to a graph. But this is very nice here for the SMILES or the selfies. We can go in both directions. So we can even solve inverse problems where we want to put in the properties into a machine learning model and let the model design a new molecule. It also works very nicely for tasks like reaction prediction or retrosynthesis, where we basically do a translation task where we translate from one input structure to a target structure or back, because all of that can be represented as strings. It's still not the most natural representation, because proximity of atoms is not necessarily encoded here in proximity of characters in this sequence here. So it's not the most natural representation of molecules, which is why this is also not perfectly suited for molecular property prediction. So the question is, can we bring the machine learning models even closer to the graph directly, or maybe even the molecule as a 3D point cloud or atom cloud itself? And yes, this is also possible, and this is where graph neural networks come in. So the idea is that we don't directly try to translate a molecule into a certain representation, but we first let the molecule or the atoms of the molecule learn their representation themselves. And this is what so-called message passing neural networks are doing. So they represent each single atom in the molecule, each single atom in space as a vector representation, and these vector representations can now start to talk to each other and exchange information. And what exactly they're talking to each other is basically determined by the neural network that's trained. So they can learn themselves what is the essential information that I have to give to my neighbors, to the other atoms in proximity, in order for them to be able to learn a useful representation of their environment, or in order for me to learn a useful representation of my own environment. So we first learn all these atom representations, and then only in the end we combine all the atom representation into one vector representing the whole molecule, and this can then be fed into a standard neural network to predict properties. And such graph neural networks are currently state-of-the-art, at least for large data sets, I have to say, in terms of performance, in predictability of how well they can infer certain molecular properties. Patrick Reiser in my group is developing a relatively convenient and easy to use library to implement such graph convolutional neural networks or message passing neural networks with a focus on application in chemistry. So if you want to try this out, please go to this GitHub page and try it out. And it's really meant to be included. For example, I was developing a project proposal with Nicole Jung where we wanted to include these graph convolutional networks in ELNs. So end users have direct access to machine learning models, can train them on their own data sets and predict molecular properties on the fly using state-of-the-art machine learning models. So how can we use them now? And now I will switch to the more applied part of my talk. So I'll show you how we can use such machine learning models either to simulate molecules to get more insight into what is, for example, going on in this case in photochemical reactions, and later on, how can we use them to predict synthesis conditions. So the second project I'm going to talk about is a collaboration with the group of Stephen Lopez at Northeastern University and his postdoc Jingbai Li. And we were looking into photochemical reactions. But before I come to that, I would like to quickly close the gap. So now we talked about how we can predict molecular properties, but now we want to simulate what is going on in an atomistic system. And for that, we need to predict energies, and from the energies, we can predict forces. And there's a lot of different methods that can do that, ranging from classical force fields for very large systems, for example, proteins, to ab initio MD simulations that can predict very complex quantum mechanical systems, for example, photodynamic reactions. But they all live on a trade-off between the timescale and the system size you can achieve with these methods due to their computational cost or low computational cost, and the accuracy or applicability that you can reach with highly costly quantum mechanical methods. And in the last decades, it was shown by people like Bela, Isayev, Tachenko, Tsesani, and others that machine learning-based methods, machine learned potentials, can basically replace the ab initio part in ab initio MD simulations. So they can replace the costly quantum mechanical simulations at a much lower cost, but almost the same accuracy as the training data. So they can basically break out of this simulation trade-off here and deliver a very highly accurate energy and force predictions at a much lower cost. So we can use them to drive molecular dynamic simulations, use these forces to update our systems and do a time evolution of the system in a much faster way than we can achieve with ab initio methods. And at the same time, we can simulate systems that are so complex that they cannot be easily simulated with classical force fields. So this is what we did now for two reactions. We looked at a cis-trans isomerization of this very simple molecule here, and at the ring closing reaction of this slightly more complex molecules, where there's also two products. And the trick, or the important part here is that we're not looking at the ground state of these molecules, but at excited states. So we start at the excited state of our starting structure, which is anyway not possible with classical force fields or similar methods. So we would need ab initio methods, but they are too costly to reach simulation times, we will see that later, that are needed to really see statistics of such reactions. So this is also all implemented and available on GitHub. So you can also check out here the codes, A for the molecular dynamics simulation itself, for the excited states dynamics, as well as for the machine learning energy and force prediction part. So now, of course, we can first of all run the simulation, implement all the methods, do everything and compare just to the quantum chemistry trajectories to make sure that everything is working and not the accuracy is good enough to reach the same results as which we would reach with purely quantum mechanical calculations. So for this simple cis-trans isomerization reaction that I've shown, we can run both all the trajectories both in the quantum chemistry way and using the neural networks. And we see that the time evolution here of the first excited state. So as I said, we start in the excited state, then this will at some point depopulate the ground state. If we average over many trajectories, we get here such a smooth behavior where all the molecules after a certain amount of time end up in the ground state, and then either again back in the trans conformer or in the cis conformer. And at the same time, of course, the ground state, the S0 population, grows when the S1 population shrinks. So we're only looking at two excited states here. So this seems to work. The quantum chemistry and the neural networks are relatively good in agreement. We get much more statistics with the neural networks, which is why these curves look smoother, because we cannot run so many trajectories using quantum chemistry. So this seems to work. We can also look at the time evolution of these states. We start here in this corner here, which is the trans geometry, but in the excited state, so the energy is high. Then most of these points or most of these trajectories go into this corner where there's these black dots. Those are the transition states where they hop to the ground state, and then they hop to the ground state and either develop to the ground state in trans configuration or in the cis. And this looks more or less the same. We get, as I said, more statistics here for the neural networks because it's much more computationally efficient, but we get the same trajectories, the same results more or less. But now we can look at the more costly or the more complex system, this ring closing reaction, where the quantum chemistry is getting so costly that we can only run a few single trajectories here. So now we cannot really compare anymore the statistics. And we also see that when we start all our trajectories up here, we don't end up in both of the end forms that we know from the experiment. So we only see trajectories here in the quantum chemistry that end up in this anti-4 configuration, and none of them ends up in the syn4. And only using the neural networks that were trained, not of course using this quantum chemistry data, but using an active learning algorithm that can basically decide itself how to explore the configuration or the conformation space and ask for new quantum chemistry data. It can also find this syn4 state that was never even discovered using purely quantum chemistry driven simulations. So it can really actively explore, starting from the starting structure, all the reactivity, all the different conformation spaces necessarily, find intermediates here, this 3A and 3B, and then also find the end states. And of course, we can now apply this to reactions where we even know less about, where we don't even know what are all the products, what are the ratios, and so on, and explore actively how these reactions would evolve on an atomistic scale if we would run them in a real experiment. We can apply this, of course, now also to other systems. We're looking, my PhD student, Chen Zhu, is looking into the stability of small organic semiconductor molecules used in OLEDs. We're also looking into biological systems. Here it's not the excited state, but the systems are still complex enough to be quite challenging. Here we're looking at hydrogen atom transfer in biological systems using these using these machine learning potentials. And Marlene Neubert, a PhD student, is looking into that in the HITS for Health Information and Data Science School from Helmholtz. But not everything can be simulated. So let's switch to the last part and let's look into the direct interaction between machine learning and experiment. So here we're looking, as I said, into a task where we want to predict the synthesis conditions for metal organic frameworks. So the typical task is you have a new metal organic framework that you would like to make, and the expert approach would now look into literature, compare the MOF structures to what is known, and find the most relevant one in its literature, make a good educated guess for the synthesis conditions like temperature, time, solvent, and so on, and then start a trial and error process where the expert would make the MOF with the guessed synthesis conditions in the lab, see what would be the yield and so on, and then iterate and refine the synthesis conditions. The data-driven way would be slightly different. So we would create once a database of all synthesis conditions that we can find in the literature. And then we train a machine learning model that tries to learn the relationship between the structure, the molecular structure of a metal organic framework and the synthesis conditions. And then it would suggest for a new target structure a given set of initial synthesis conditions, given based on the learned similarities or the learned representations of MOFs. And then, of course, we can start again using this model refinement process to get experimental data from the lab, get feedback, okay, this did work, this didn't work, add this to the database, refine the model. So every time a new experimental data point is coming in, the model will be refined, get a better estimate, and therefore adjust itself or improve itself until it can predict what is the best synthesis conditions for this MOF. So this is what we did. We created a so-called SynMOF database where a postdoc of Manuel Tosala's group was developing an algorithm to automatically extract MOF synthesis recipes from the literature. We were extracting what is the solvent, what is the temperature, the additive, and the reaction time. And then we automatically extracted also information about the molecular structure, the metal type, organic linker, and so on, from the CIF files, the CIF structure files, which are available for all of these MOFs. And this is all included in the database. And now we trained a machine learning model that uses the structures, the metal type, and the linkers as some representations as input. We could not yet use graph neural networks here because the database is simply too small at the moment for graph neural networks to be efficiently trained. We used a mixture of different representations, as I mentioned before, like the chemical fingerprints and so on, to be fed into a normal neural network. We also tried different machine learning models to predict temperature, time, solvents, additives, and so on. This works. It doesn't work perfect yet, I have to say. So the correlation between the predicted temperatures and times and the experimentally reported ones is relatively low. But this low number is also due to the fact that there is no such thing as a real true answer, because synthesis conditions that are reported in literature are not just exact temperatures, but they're always like a range. There's not a true answer. It's exactly 100 degrees. It could be also 120. The ranges are quite large. We don't know if everything is optimized. So we cannot expect that the model will ever have a perfect correlation between what is reported in the literature and what is predicted. But also what made us a bit surprised, we compared this to experts. We wanted to know how much worse is our model compared to expert predictions. So we asked a lot of postdocs and professors with a lot of experience in MOF synthesis, what would be given a new MOF, what would be the ideal temperature or time to synthesize. And here there was almost, I have to say, unfortunately, almost no correlation with what was reported in literature. So it's really a very, very hard task, even for experts, to just look at a MOF structure and then estimate what would be a good temperature or time for the synthesis. But what we see here on the right, what is rather promising, is that the mean absolute error, so the performance of the model as a function of the number of data points that we have, is decreasing relatively fast. Our database currently only has 600 something structures, so it's relatively small yet. But for example, the neural network method here is relatively steep. So with more data, just 1,000 points, 2,000 points, and so on, which is absolutely feasible, given how many MOFs are reported in literature, we could get much better performance. We just need to further increase our database. Everything is also available currently. You can go to this website and try it out yourself. So you can upload there your desired MOF structure that you can find in some MOF database that you would like to make. And in the background of this website, then the CIF file will be translated to our machine learning input vectors. The machine learning models will be predicting the temperature, time, and so on, and it will tell you what is the ideal synthesis conditions for this desired MOF. And this is exactly what we are also now doing in the lab. In Manuel Zazala's group, we use the tool to predict synthesis conditions for MOFs and test this out, how well it actually works as a first guess. With this, I'm at the end of my talk. I talked today a lot about how we can represent chemical compounds for machine learning models and how graph neural networks can help a lot here to predict better properties. Discussed a bit how we can use simulations based on such models to really get more insight into chemical reactions. And then in the end, I've shown you how we can use the same models also to predict synthesis conditions in order to speed up the experimental discovery of new materials. And with this, I'm at the end of my talk. Thanks again to all the group members who contributed to this work, to all the funding organizations. I thank you for listening.